Bismillahirrahmanirrahim. Let's start our next lecture for heat and mass transfer. We are going to start chapter number 2 of our book, the title of which is Introduction to Conduction. Although we had a good introduction to conduction in the previous chapter, so over here in this chapter the only topic that we would be covering is in fact the heat diffusion equation. We will see what that heat diffusion equation is, and we would be going over the heat diffusion equation in the three coordinate systems: the Cartesian coordinate system, the cylindrical coordinate system, and the spherical coordinate system. In Cartesian coordinate system, we would be considering the heat transfer in x, y and z directions, means there would be a wall, right? And in cylindrical coordinate system, for example, let me give you an example of cylindrical coordinate system. Suppose that if there is steam passing through a pipe, so that would be the case of cylindrical coordinate system. And if there is heat transfer through a spherical shell or through a spherical vessel, so then we would be making use of a spherical coordinate system. Let's start with the Cartesian coordinates. In fact, we have a cube or a cuboid in which there are 6 faces, and you can see that there is a left face over here, and then there is a right face over there. So this is that left face and this is that right face. So if the heat is flowing in this particular direction, so we would then call it the heat flow in x direction, if this is our x direction. So if the heat is flowing in, for example, x direction, then it will flow from this left face to this right face, towards this right face. Similarly, if the heat is flowing from this front face to that back face in this direction, so we would consider heat transfer in y direction if the heat is flowing from the front face to the back face. And if the heat is flowing from bottom face to the top face, means in this direction, from the bottom face to the top face, then we would consider it as the direction. So left to right face, x axis, front face to back face, y axis, and bottom face to top face, z axis. So these are the 3 axes that we will consider in Cartesian coordinate system. And the heat flux in x, y and z directions may be given as minus k dt by dx, minus k dt by dy, or minus k dt by dz using the Fourier's law of heat conduction. And if the heat transfer is taking place in more than one directions, means if temperature is a function of at least 2 dimensions or maybe all 3, means if t is a function of x as well as y as well as z, so then we will replace that d sign with a partial differential Dava sign. Now let's start considering a differential element. Differential element is in fact an element out of the whole system, out of the whole wall, out of the complete wall. So we are considering a differential element, means a very small element, the length of which is dx, the depth of which is or width of which is dy, and the height of which is dz. So we have this differential element. Kindly note that this is the same thing as the cuboid that we were discussing on one of the previous slides. So the heat will transfer. So now if the heat is being transferred in this direction along the length, so then it will move from that left side face to this right side face. And if the heat transfer is taking place in this direction, so then it will be moving from that front face to the back face. And if the heat is flowing in this direction, then it will move from this bottom face to the top face. So we have considered an infinitesimally small differential element, control volume, having dimensions of dx, dy and dz. There is no bulk fluid motion involved, means we would be considering conduction. Only thermal forms of energy will be considered, of course, because we are learning heat transfer. And if there are temperature gradients, then conduction heat transfer will occur across each of the control phases, means the heat will transfer in x direction if there is a temperature gradient in x direction. If the temperature of this left phase and the right phase are at different values, if the two phases are at the same values, of course, then there won't be any temperature gradient, and therefore heat will not be transferred in x direction. So for the heat transfer to take place, there must be temperature gradient in that particular direction. Now, for that same differential element, we start with Qx, means if we say that the heat or energy that comes in x direction is Qx, it will come into the left side phase, and the heat that goes out of this control volume from the right side phase is Qx plus dx. So this is Q suffix x, and over here we have x plus dx in the suffix of Q. So Qx comes in and flows over a length of dx, so therefore Qx plus dx is the amount of heat that will flow out of this control volume. Similarly, Qy and then Qy plus dy. So Qy is the amount of heat that comes in to this control volume in y direction from the front phase, and Qy plus dy is the amount of heat that will leave this control volume from the back phase, not from the top phase, from the back phase. And then in the last, Qz is the amount of heat that will come into this control volume through the bottom phase, and Qz plus dz is the amount of heat energy that will leave this control volume from the top phase in z direction. So again the 6 phases. Over here it would be a little bit easier for you to visualize that this is the phase that will receive Qx, and this is the phase that Qx plus dx will leave. Similarly, Qy will be incident on this front phase, and Qy plus dy will leave the back phase, and Qz will come in through this bottom phase, and Qz plus dz will leave the top phase. So heat transfer in x-axis, heat transfer in y-axis, heat transfer in z-axis. This is another figure from our book. Over here you can see that we have got the same differential element having dimensions of dx, dy and dz as described previously, and this differential element is a part of the complete system. As I explained earlier, it is a part of a larger system. So over here we can see this Qx, we have this Qx plus dx, we have this Qy, energy coming in y direction, Qy plus dy, energy going out in y direction from the back phase, and similarly we have Qz and Qz plus dz. So Qx, Qy and Qz are the energies that are coming into this control volume, and Qx plus dx, Qy plus dy and Qz plus dz are the energies leaving this control volume, However, in addition to that, we have got two more energies, E stored and E generated. E stored is the amount of the energy that the system will store. The system may store energy, the system may not store energy. Now if there is energy storage in the system, that would mean that the system will keep on absorbing energy, as a result of which its temperature at a particular location will rise. And if the properties at a particular location do not remain the same with respect to time, rather they change with time, then that system will not be considered under steady state conditions. It will be under transient conditions. So if there is energy storage, the system will definitely be under transient conditions, and if there is no energy storage, then the system will be considered under steady state conditions. And energy generated. Energy generated is the amount of energy. For example, if we have this block, we have this wall, and suppose there is a wire which passes through this wall, and if we let the electric current pass through this wire, so heat will be dissipated inside. So that is the phenomena that we call energy generation. So we have got an energy in, we have got an energy out, we have got an energy stored, and we have got energy generated. So we have got 4 components of energy over here. All 4 may exist in a particular system, or a lesser number or a few may exist in any system. So let's start the derivation with the energy balance. Energy balance says that energy coming into this control volume plus energy which is being generated inside the control volume are the 2 ways through which the energy can come in, and it will be utilized in 2 ways. Either the system will store energy, or the energy will leave the system. Kindly note that we will keep all 4 for the sake of the derivation. But in some real cases we may not have all 4, we may have all 4, we may not have all 4. So we would be deriving the equation, the heat diffusion equation, considering all 4 types that are being mentioned over here. However, if there is a simpler system, for example, if you are told that the system is working under steady state conditions, then E stored will become 0, right? However, in the beginning we won't be making any assumptions. So now the energy in is Qx, Qy and Qz in x, y and z directions respectively, and then the energy generated. Energy generated over here is represented with a Q dot, but that energy generated is on per unit volume basis. So all we need to do is simply multiply this Q dot by the volume of this control volume, which is dx times dy times dz. Energy going out in x direction is qx plus dx, in y it is qy plus dy, in z direction it is qz plus dz. And the last term, which is the energy stored, many of you might already have figured out that energy stored would be given as mc delta t. But over here Q have got the units of watts, whereas mc delta t has got the units of joules. So therefore, if we multiply this joules of mc delta t by time and make mass as mass flow rate then the units of m dot c delta t will be the same as that of Q, means watts. Now in the next step, the left hand side of the equation remains the same. The right hand side of the equation requires some discussion. Qx plus dx is written in this form. Qx plus dx is written in this form. Qx plus dou q by dou x times dx. In simple language, it is unitary basis method, and scientifically we call it Fourier's expansion. See, what does it say? Qx plus dx is qx, means qx plus dx is equal to qx, whatever came in x direction, plus dou q by dou x. Dou q by dou x means change in q in x direction. Dou q by dou x means change in the heat flow in x direction. But this dou q by dou x will give us the change in heat flow per unit of x. So all we need to do is multiply this change per unit x by the total x, and the total x that we have in x direction is the length, which is dx. Similarly, qy plus dy can be written as qy plus dava q by dava y dy, and qz plus dz may be written as qz plus dava q by dava z times dz. The last term, which is mc delta t or m dot c delta t, is written in this form. See, we have written delta t as dava t, and we have brought the time component of mass flow rate into the denominator of temperature, thereby writing it as m, mass. And since we can see that the heat is being transferred in x direction, in y direction, and in z direction as well, so temperature would therefore be dependent upon more than one variables. Temperature would be a function of x and y and z and time. So therefore we are writing it as dava t by dava t and not dt by dt. What will happen then is that the qx will get cancelled out, the qy will also get cancelled out, and qz will also get cancelled out. So on the left hand side we will be left with q dot times the volume, and on the right hand side we will be left with dava q by dava x times dx plus dava q by dava y times dy plus dava q by dava z times dz. Now the last term, Cp remains Cp, dava t by dava t remains dava t by dava t. Mass is by definition density times volume, because density is by definition mass times volume. So density has been written as rho, and the volume has been written as dx into dy into dz. Then writing equation 4 again, because this is our starting point on the next slide. What we will do is that we will write the left hand side of the equation remains unchanged, whereas we will do some mathematics on the right hand side of the equation. See, we have dava by dava x of q, and q is written as minus ka dava t by dava x as per Fourier's law of heat conduction. And then we have dava by dava y of qy. So qy would be minus ka dava t by dava y by Fourier's law of heat conduction. Similarly, dava by dava z of qz, and qz is minus ka dava t by dava z times dz, and the last term remains the same. Over here you will notice that we have written a as ax, ay, and az for the very simple reason. See, if we look at this diagram, qx is being incident upon the area which is dx times dy, whereas qy is being incident upon this area which is dx times dz. So the area on which qx is being incident upon is not the same as the area on which qy is being incident upon. Similarly, qz is being incident upon the face, the area of which is dx times dy. So since qx and qy and qz are being incident upon different areas, so therefore we have written ax, ay, and az. And as I just mentioned you that ax is dy times dz, ay is dx times dz, and az is dx times dy. So in the next step we will write the corresponding areas. Now since over here we are differentiating with respect to x, so y and z will be taken out of the differential sign. So therefore y and z, dy and dz will be taken out of the differential sign, and we will be left with dava by dava x of k dava t by dava x. And then since over here we are differentiating with respect to y, so therefore x and z will be taken out of the differential sign, and we will be left with dava by dava y of k dava t by dava y, dava by dava y of k dava t by dava y times dy. Similarly, since we are differentiating with respect to z, so therefore we will take out dx and dy, and we will be left with dava by dava z of k dava t by dava z times dz, and the last term remains unchanged. Now you will notice that we have dx, dy, dz in every term of this equation. So in the next step we will divide throughout by the volume of this control volume of this differential element. So if we divide by the volume throughout, so we would have q dot on the left hand side of the equation, and we would have minus dava by dava x of k dava t by dava x, the first term on the right hand side of the equation, and then the same or similar term in y, and then the similar term in z. And in the last term, dx, dy, dz will get cancelled out, so we will be left with rho c dava t by dava t. We have rho c dava t by dava t. Now we have got three negative terms on the right hand side of the equation. So if we if we take those terms on the left hand side of the equation, just to write them with a positive sign, so we will have dava by dava x of k dava t by dava x, dava by dava y of k dava t by dava y, plus dava by dava z of k dava t by dava z, plus q dot is equal to rho c dava t by dava t. This equation is called the heat diffusion equation in Cartesian coordinate system. You might be wondering, first of all, you see the if you see the similarity, if you only focus upon the first term, then the second and the third terms are similar. All you need to do is write y in place of x, and then z in place of x or in place of y, and then plus q dot is rho c dava t by dava t. So this is a pretty simple equation. It is called the heat diffusion equation in Cartesian coordinate system. You might be wondering why we have got this k thermal conductivity inside the partial differential sign. See, if we are keeping it inside, it means that k is having a different value in x direction, a different value in y direction and in z direction. Means the material is not isotropic. The material is anisotropic. Means we have got a kx, ky and kz. So if this is so, then k will remain inside the differential sign. However, if it is not so, means if we take the k out of the differential sign, saying that the material that we have is isotropic, so then we will have dava by dava x of dava t by dava x, taking k out of the differential sign, and then dividing throughout by k at the same time, plus dava by dava y of dava t by dava y, plus dava by dava z of dava t by dava z, plus q dot over k is rho c upon k dava t by dava t. Now k over rho c is thermal diffusivity, as discussed before in one of the previous lectures. So in the next step we can then write this k over rho c as alpha or 1 over alpha. K over rho c is alpha, so therefore rho c upon k would be 1 over alpha. So this is a version of the heat diffusion equation. I would advise you to keep this one in mind, the basic version, because all other things, all other versions can be derived depending upon the circumstances, depending upon the conditions provided. Now starting with this thing, second derivative of t with x plus second derivative of t with y plus second derivative of t with z plus q dot over k as 1 over alpha dava t over dava t, starting with this equation. And if we impose four conditions, I do not want to say assumptions, but rather if we impose four conditions. And what are those four conditions? If we say that we have got one dimensional heat transfer, means temperature will vary either in x only or in y only or in z only. If there is no internal heat generation, means q dot is 0. Steady state system. Steady state system means the properties will not change with time. And constant properties. Constant properties means, of course, the thermal conductivity is being considered as a constant quantity. So if there is a one dimensional heat transfer, and if we say that temperature varies in x only, you may keep y or z, it's your choice. But if we say that temperature is a function of x, so then this term and this term will vanish because of that one dimensional heat transfer. No internal heat generation means q dot is 0. And if the system is working under steady state conditions, it means that no property will change with time. So dou T by dou T would become 0. So we will be left with second derivative of t with x as 0. And we can then replace this lava with a d. Because now since temperature is a function of x only, it is not a function of y, it is not a function of z, and it is not a function of time. Then this thing may be written as d by dx of dt by dx is 0. Second differential of temperature with x is 0. Now what does this mean? It means that temperature is having a linear function and heat flux is therefore constant. Now how can we deduce, how can we say that temperature is having a linear function? See, if this is the plane wall that we are talking about, and if we say that temperature is a linear function of x, means temperature is a plus bx or y is equal to mx plus c. So if temperature is a plus bx, what is the first derivative of x? B. And what is the second derivative of x? 0. So the second derivative of x of t with x would become 0. So what does this mean? It means that if it is one dimensional heat transfer, if there is no internal energy generation in the system is working under steady state conditions, and if the thermal conductivity is constant, then the temperature would be varying linearly. And if any of those four conditions is relaxed, for example, if you say that there is internal heat generation, then the temperature distribution will no more be linear. Rather it may be a plus bx plus cx square. Now let's have a quick discussion on one dimensional heat transfer. See, if we consider the heat transfer in x direction only, so it would mean that the heat will be transferred in this direction only, in x. It means that the temperature gradients exist only in x direction, and the temperature gradients will not exist in y or in z direction. So one dimensional heat transfer is not an assumption. Rather it is a case, it is a condition that the system is having. So if the system is such that the heat is being transferred from the front face to the back face, it means that the heat is being transferred in y direction. It means that the temperature gradients, temperature difference occur only in y direction and not in x or not in z. So one dimensional heat transfer is not really an assumption, rather it is the condition which the system is facing.